welcome back. So today we're going to finish up the external flow stuff and talk about the form drag. We left off with the turbulent flow boundary layer, and laminar boundary layer, and just the boundary layer concepts, which helped us talk about skin friction. And there was the other type of friction, form drag, and that's what today is. And that will conclude external flow. It's mostly all concepts that we talk about in this class about external flow. You don't have a lot of homework calculations involving external flow, so I think more importantly are the concepts of where these relationships of Reynolds numbers come about. And then the form drag stuff is different, but you'll see. So, on to the form drag. So, just like we had in internal flows, right? We studied valves, and curves gave us these loss coefficients as well. So very analogously, right, for the external case, what we're going to study, we're going to have this idea of curved surfaces, which will lead to pressure drops in the case of something called separation. So you're seeing a lot of the same things come about from the internal to the external, but you're going to see now how the curvature of a surface affects the pressure distribution on it. Pressures means forces. Forces give us power, so that's what we want to get at, right? So what is drag force, right? That's the question I always want to answer. So you have this body that velocity. You have this normal vector to a surface and then a tangent vector to a surface. So I use this for a body. This is some region that is solid opposed to fluid out here. So this is fluid. Then I always use this notation from math. This is the boundary of your solid surface. Okay, so that's the picture that you have. Now, drag force is an integral relationship where it's the pressure field and then normal vector to the surface dotted with a little bit of area. This is over a surface. This is the shear force that we have. Okay, so this is the tangential vector at every point on the boundary of the surface, dotted with a little bit of area. So computers do this really well. And then at each of those points, you scale that up by the shear stress. So as you recall, right, the whole point of the skin friction stuff was to get this value and get approximations based on it. So what does that mean? That would mean that, like, if you have a body and out of every single point of the body, right, you could think about a little bit of area. You could think about the Reynolds number behaving at that point using boundary layer analysis. That would give you this scalar constant, and then this stuff is just worked out from the geometry or the solids work product you give the body. So that kind of takes care of this, right? So sort of this. That's why we calculated those skin friction coefficients, and we did it pretty heavily. And what were they like? They were like the Moody diagram. It even kind of looks the same because it's something about viscous, right? Something about that viscous losses. It should kind of look the same. It's really like what's internal versus external if you're really close to a pipe wall. But this term we left out, and that's what we talk about now, right? And this is the form drag. If the plate's flat, then this is zero. Now, why is that the case? Well, if the plate is flat, then here's my normal vector, right? And then you have this pressure. So these little bits of area right here right? So then they're perpendicular, so it's always zero. So you don't really get that term behaving in there. And you get this idealized boundary layer. But if there's any curvature at all, this will happen, and then you get some other effect that we'll talk about called separation. So this is very dependent on the geometry of the body. This is what drives it. And again, you have this scalar field that you're scaling up this quantity by. That being said, let's go along with how do we analyze that, and you're all going to come down to the streamlines going over the body. So here's the external flow. Far away, it's parallel and viscid flow. It just kind of looks like still air moving forward. It interacts with the body. You always draw an airfoil because that's the classic. So you have some scenario that's looking like this. Okay, now think of this now as a u infinity as a function of some parameter, a streamline coordinate that's right. Think of it as like right here, s equals 0, and then you could have it here, s equals like 1. Doesn't matter what the units are, but that's a streamline coordinate. So that's fundamentally now. That's the difference, right? The difference now is now that this free stream velocity changes based on the coordinate. S is a function of, right, x is even you could do a parameterization of y and x. It's actually s can be parameterized with that. It doesn't really matter. The fact is now this free stream velocity now is changing. Sort of think of it as before, in the simple flatline case, it was always a function, but it was a really boring one. It was just a constant function. But for curved bodies, now this thing has to change as it goes along the streamline. So how does that affect pressure? So I think I have a note. So the idea is, right, here, the point of the boundary layer, right, was what? Is inside here, right, or that separation region, is we have viscous, right? This is blown out of proportion. So you have viscous flow under that free stream. Then above, it looks inviscid. Right? You don't see the effects of viscosity once you hit this free stream velocity. So this idea of a changing streamline coordinate is the same idea as if you have your flat plate. If you look up really close to it, you draw the exact same picture before. And when you reach here, the idea is this top part is now changing. So think about like you could kind of see how this reacts if you move it forward or backward, the front of this thing. Because when I get to this free stream velocity, it as well changes. It doesn't just reach some constant value. It's now a changing quantity. So that's the idea. If I zoomed in really close, what's happening is I have boundary layer points, and then I get up to my viscous, and then I get up to my inviscid part. The inviscid part itself changes as it goes back and forth. So you have two layers of changing quantities. That's the idea to have in your head. More importantly, all that matters in this class is you realize that in this section right here, an equation I can put to this u of s, I understand, since this is inviscid, and even, right, we can say that it's inviscid. We'll say that this is inviscid, and this is not, we'll just say, right, it's pretty motivated that outside it's inviscid, and then we'll say irrotational. Right? And that's also motivated as well. If you just look far away from a free body, you go like, oh, on the outside it's like potential flow, which is something we don't even cover anymore. But these assumptions are what allow you to get to say, okay, I can use the Bernoulli equation then. Right? And that's a Bernoulli equation along the streamline with the s coordinate. What does Bernoulli say? Bernoulli is a conservation of energy, right? This pressure. Conservation. So it's saying along my streamline, this quantity is conserved. Quantity here, as it is here, is the same as the quantity is here. You've been using it a bunch, but you just have to think of it as you're just tracking that exterior inviscid part of the boundary layer flow. So this is some conserved quantity. So the pressure can change. You can just put these things. And even this Z, right, even this, I should put a Z there, I'm very bad, sorry. So I think if even this Z could change as you go along. It's really just how this normal vector changes with the Z. But you'll see that that doesn't matter as well either. Okay, so that's the setup, right? We've gone from skin friction, how do we get pressure distribution forms? Well, the pressure is going to be changed by this outside part of the flow, not the viscous part of the flow. And that's how we studied foils for the longest time, I believe, was we didn't even consider the viscous part. We just did this type of analysis because we looked in the inside going, it can't be too much, so forget about it. Turns out if it's really big, if you have a big enough streamlined body, it can be a considerable skin friction force. But, right, if it's small enough or there's ranges where it didn't really matter, so this is sort of the older analysis of lift and drag on foils and external bodies.